In this lecture, we will see how to construct manifolds by gluing open subsets in Rn. Okay, so before we start with manifolds, let us understand what it means to glue topological spaces. So we can take an easy example. Uh, let u equal to r and v equal to r. Let's call this u0 and u1 and u2. I'm taking two copies of r, and let u12 inside u1 be the set. I just remove 0, and similarly let u21 inside u2 be the set so let phi12 from u12 to u21 be the map t goes to 1 upon t. Then phi12 is a homeomorphism. So using this homeomorphism, we may glue u1 and u2 along the open set u12 and u21. So what this means is that, so I take one copy of R, so let me make it vertically, and I remove my origin, and I take another copy of, so I take one first, I take two copies of R, and I remove the origin. I mean, outside of, on R minus 0 on both of these, I identify T with 1 upon T. So let's say this is my 1. So if we view this copy of R like this, and this copy of R like this, then it's easy to see that this point here is getting identified with this point, and this point here is getting identified with this point. So when we join these two using phi12, so this implies we will get the topological space. We will get this topological space. So uh, so this so this so I haven't so the topology on X is defined as follows. So let's call this X. A set U is said to be open if U intersection UI is open in UI. So what this means is the following. There are two subsets of X. There are two subsets. Well, let me define X formally first before defining the topology. As a set, X is equal to U1 disjoint union U2 modulo equivalence, where X is identified with pi12 of X. So in particular, uh, so in particular, X uh, has to be in U12 to be identified with anything. No, I don't need this. So there is a natural map. There are natural maps U1 to X and U2 to X, and it is clear that these are inclusions. The topology on X is defined as follows. A set U is open. So let's give these maps some names. Let's call this I1 and let's call this I2. If and only if I1 inverse U is open in U1 and I2 inverse U is open in U2. Okay, so and it is easy, it is clear in this example. It is clear that as a topological X is homeomorphic to S1. More generally, so more generally, the gluing construction is done as follows. Suppose we have the following data. Topological spaces ui for I inside some indexing set I. For each pair I comma j, we have open sets uij contained inside ui and such that uii is equal to ui. 3. We have homeomorphisms phi ij from uij to uji such that phi ii is equal to identity of ui. And lastly, for all I j k, we have phi j k compose phi I j is equal to phi I k on uij intersection uik. So then we can construct a topological space. Okay, let's construct a set first. The set X as follows. X is defined to be the disjoint union of all the ui's modulo equivalence, and the equivalence is X is defined equivalent to be phi ij X. So there are natural maps ui to X. So let's call these maps FIs, and it can be checked that the FIs are inclusions. And we define the topology on X is defined as follows. We define a topology on X by setting U, a subset of X, to be open if and only if Fi inverse of U is open in Ui. So the condition phi jk compose phi ij is equal to phi ik on u ij intersection u ik is called the cocycle condition. So this condition is naturally motivated as follows. Uh, as we see now. So suppose we start with a topological space X, which can be written as the union of three open sets U1, U2 and U3. So my X is U1, U2 and U3. So let us treat, let's give the inclusions name. Let Fi from Ui to X denote the inclusions. Now, if you look at U1 intersection U2, which is over here, then there is a map phi ij from U12 to U21. So U12 is I'm viewing the intersection as sitting inside U1, and U21 I view the intersection as sitting inside U2. So this map is, in this case, it's just the identity map. And similarly, so this is my U12 and this is my U21. So my phi 12 is like this. Similarly, I have phi 13, and here I have this is phi 23. So notice that if I take a point over here, so this area, this region here, this small triangle, that is U, this small triangle is U12 intersected U13, and this triangle is going to get mapped to this triangle here. So this triangle here is U21 intersected U23, and this triangle under phi 23 is going to get mapped to this small area. And if I take any point over here, well, in this particular case, all these maps are identity maps. So this point gets mapped to this point, and this point gets mapped to this point here. And obviously, under phi 13, this point should get mapped to this point. So the cocycle condition is very naturally motivated. So that's all that I want to say about this right now. Okay. So suppose we are given a map of sets phi from x to y, then it is easily checked that it's almost by definition phi is continuous if and only if when I compose fi, or this is just the restriction phi restricted to ui, or which is equal to phi compose fi, is continuous. Okay, so this is basically, this brings us to an end of gluing for topological spaces. So now let's see how to use this construction to make sense of manifolds. So here what we have to do is, okay, so first let U contained in Rn be an open subset. Then we know what smooth functions, real or complex value, on U are. So we will assume that we know this definition, and 2, suppose we are given, so this definition is a prerequisite for this course, so I will assume that you know this. Suppose we are given open subsets U contained in Rn and V contained in Rm, and a map phi from U to V. So then we know what it means for phi to be smooth. Namely, my phi from U to V will be of the type phi x maps to phi 1 of x, phi 2 of x, and so on up to phi m of x, where x is an n tuple x1, x2, xn, and phi is smooth by definition if all the phi i's are smooth. So now suppose we are given the following data. One, open subsets ui contained in Rni. 2, I in some indexing set. For each pair I comma j, there are smooth homeomorphisms phi ij from, okay, before that, for each pair ij there are open subsets uij contained in ui such that uii is equal to ui 3. For each pair ij, there are smooth homeomorphisms phi ij from uij to uji such that phi ii is equal to identity of ui. And 4 on the open subset phi uij intersection uik, we have phi jk compose phi ij is equal to phi ik. So if we have this data, let us make a few remarks. So some remarks. A, if uij is not empty, then R, then Ni is equal to Nj. So here the uij's were contained in ui's, and the ui's in turn are contained in Rni. So this is a standard result, so which says that if u contained in Rn and v contained in Rm are two open subsets, such that they are homomorphic, then M is equal to N. That's one remark. Next remark, let's see. So since phi ij is a smooth, okay, so when I apply the, so taking k equal to I in the co-cycle condition, we see that phi ij, phi ji compose phi ij is equal to phi ii on uij. So in particular, this implies that the map phi ij, which was fully assumed to be a smooth homeomorphism, is actually a diffeomorphism. That is, its inverse is also smooth. So this is not true in general, right? Because we can take the example phi from R to R given by x goes to x cubed. So this map is a smooth homeomorphism. It's a smooth map and it is a homeomorphism. But the inverse is not smooth at the origin, at 0. Okay, so having made these two remarks, we can define, define a topological space X as follows. As before, X is the disjoint union of ui's, and modulo the equivalence X is equivalent to phi ij X. And but now X also has a smooth structure. So what do we mean by this? So for example, we can define smooth functions on X. Okay, so let's first define smooth real valued well, we can define smooth functions, real or complex value. So how do we do this? So suppose I am given we can define smooth functions not just on X, but also on open subsets of X. So what do we have to do? So suppose we are given a map of sets F from U to say R or C, depending on whether you want to take a complex valued or smooth valued function. Right. So define F to be smooth if the composite ui intersection U to R, it's my F or C, is smooth for all I. Similarly, okay, so so suppose we have two such manifolds, X and Y, then we may define the notion of a smooth function, of a smooth map from X to Y. So how do we define this? So suppose X is obtained by gluing open sets, by gluing sets UIs subsets of R. These are open sets of R, some Rn's, and Y is obtained by gluing open sets Vj's. Then we have Vj. We look at phi inverse Vj, and inside this is contained Ui intersected phi inverse Vj. So let me make a slightly bigger picture. X, Y, phi inverse of Vj, Ui intersected phi inverse of Vj, and this this is a subset of some Rn, and this is a subset of some Rm, and we know. So now we apply the definition of smooth maps between open subsets. Subsets of Euclidean spaces of Rn's. Okay, so phi is open if and only if, this is the definition, when I restrict it to this, I'm sorry, not open, smooth. Is smooth for all pairs I, j. So let's just define what a coordinate is. So suppose we are given a manifold X obtained by gluing UIs, then the subsets UIs are called charts, and these UIs, they are contained in some Rn, and on Rn we have functions, we have the coordinate functions x1, x2, xn. So this set Ui along with the functions x1, x2, xn is called a coordinate chart. So thus our manifold X is covered by coordinate charts. Okay, so we will stop here.